connecting x1, x2 with x3, or x1 as a function in x2, x3, the problems that we saw previously. Okay, but if we try to solve a non-homogeneous system, which is ax equal b, what I want to get from here is I will have the three cases. If I'm trying to work with the row operation, getting the augmented matrix, whatever, which is going to be A, then B the right side of the given equations, you will have either unique solution, which consists, we can call it a consistent independent solution, and this will happen if x find a particular values. So there is just only a particular set of values for x1, x2, x3 that will oblige this system to equal to b. And simply, in a rank 4, the rank of A should equal to the rank of the augmented matrix. If you remember, if we try to solve a system of equations, okay, just in a second, I want to make this thing clear or more clear for you. What I want to say is that if I have ax equals 0, which is a homogeneous system of equations, you will be in two alternatives. Either succeeding in getting an augmented matrix, if I talk about 3 by 3, just for simplicity, to be 1, 0, 0, 0, 1, 0, 0, 0, 1, and all the elements equal to zeros, this, and that's in x1 equal x2 equal x3 all 0, and this is the trivial solution. Otherwise, you will have for example, 1, 0, 2 equals 0, depending on the system by itself of these equations, which are 0, 1, negative 1, and 0. Then you will have all of these zeros, and in this manner, you will get x1 as a function in x3 and the x2 as a function in x3, which represent a vector, a sub-vector space for the results. Okay, and this is what we mean about the first part that I won't show it to you. But in general, if I have ax equal b, the first step is to form the augmented matrix. If you remember, this is A, the coefficient, and that's B, the column of results, which exists on the right-hand side of any system of equations. Now, for the time being, F, and I will call all of this the augmented matrix, F, the rank of A, which is the coefficient matrix, equal the rank of the augmented matrix, equal the number of unknowns, then you will have a unique solution. Which means, and this will happen only if you succeed in transferring A to be a unit matrix. And we already blah 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 know a lot about this. Going into the elementary matrices, the row operations, and so on. But F R of A, which equal to R of the augmented matrix, but less than the number of variables, you will have a set. And the solution set in this case will be the right values, which are going to change to be, for example, b dash, if you succeed in getting something like this, whatever the value here, 0, 1, anything like 3 and another value. So you will have some particular results plus this matrix, which will form the relation between x1 and x3, x2 and x3, and this is what we will see down the road, which depend on x3, and there is some numbers. That's what's exactly written here. Okay, if I have unique solution, so you have consistent dependent solution. If x equal to particular value, and this will happen if a rank of A equal the rank of A plus B. Okay. You will have infinite number of solution or consistent dependent system, and it equal to x particular values. Here is the particular values that I'm talking about, plus generating set representing relation between variables, exactly like this part. So, in general, if you have an infinite number of solutions, you will have a column which is the particular values plus the generating set of the variables that depend on each other, which will depend on the degrees of freedom related, how many variables depend on the missing variable. Okay. Or no solution inconsistent system, and this will happen directly if you have the rank of A doesn't equal to the rank of the augmented matrix. In Arabic افتكر ان لما بحل نظام من المعادلات، لو النظام بتاعي متجانس يعني القيمه اللي بتساوي صفر على طول بقدر الاقي x1 x2 x3 ممكن يبقوا بيساوي زيرو لو المعادلات دي مختلفه كلها عن بعضها، وده تريفيال سوليوشن. لو المعادلات دي ديبندنت واحد فيهم بيعتمد على الثاني اقدر اطلع x1 و x2 دايركت x3 وبالتالي اقدر اوجد ريليشن. دي الريليشن بتهمني، دي اللي انا بسميها الجنريتنج سيت. مجموعه الريليشنز دي انا عندك انفينيت نمبر اوف سوليوشنز، تحط x3 يطلع لك سوليوشن، تحط x3 فاليو ثاني يطلع لك انذر سوليوشن اند سو. طيب الست دي هي الجنريتنج سيت للسوليوشن سبيس. طيب لو انا عندي بقى ان جنرال سيستم ax ايكوال b، يعني ده الحاله العامه، يبقى انا عندي ثلاث حالات. بس اللي يهمني فيهم قوي واللي عايزك تخلي بالك منه الانفاينايت سيت اوف سوليوشن او الانفاينايت نمبر اوف سوليوشنز، والعدد لا نهائي من الحلول. لان دايما العدد لا نهائي من الحلول لما يبقى السيستم بتاعك نوت هوموجينيوس بيتكون من بعض ارقام زائد او ناقص فاريبل مضروب في ارقام. مجموعه الارقام الاساسيه دي ده اللي انا بسميه البارتيكولار سوليوشن، والجزء الثاني اللي بيتكون نتيجه ان في فاريبلز بيعتمدوا على الفاريبلز الثانيين هو ده اللي انا بسميه الجنريتنج سيت اوف ايكويشنز. مور ذان بيرفكت. يبقى اذا دلوقتي انا عندي null row and column spaces. دي النقطه السبيسيفيك اللي انا هتكلم عليها بقى دلوقتي. الجزء او السوليوشن بتاع ax equal 0 الانفاينيت نمبر اوف سوليوشن بتاع ax equal 0 ده اللي انا بسميه النل اوف a. لذلك هتلاقيني كاتب النل سبيس اوف a and denoted by null a. This is what we mean about it is the solution of the homogeneous system of the A matrix, which is the matrix formed from the vector basis of a subvector space times x equal to 0. Once you try to solve this system, this homogeneous system of equations, the result will be the null of A. If you want to get a null of A, as we will see in the coming example, all I have to do is to take these vector spaces, vector set, the basis of a vector space, putting them into a matrix, trying to work your magic, trying to get it on the echelon form. The final result will present the set of vectors which are called the null matrix. Once more, the vector space of Rn corresponding to the solution set of the homogeneous set associated to A. That's null A is equal to x belongs to Rn such that ax equal to 0 and it's a subset from Rn. Okay. Remark, for any system of equations, we have a matrix which is m by n. M stands for the number of equations and the n is the number of unknowns. Once you have a system of equation, this is the first equation, second, third. And the columns, the first unknown, second unknown, and third unknown. So n mainly stands for the number of equations and n the number of unknowns in a system of equations. If I want to get the space of the row of A, it is the vector subspace of Rn generated by the row vectors of A. That's row A equals span R1, the first row in A, second row in A up to Rn, which belongs to Rn. Once you get to the echelon form, which is the equivalent form of A, I can back the non-zero rows and those will form the space of, the basis for Ra, or rows of the coefficient matrix A. Similar manner, once we get up to the echelon form, I will take the pivots as you will see, and these will be the column space of the vector A, which is called column A. So the column A in the span of the first column of A, second, third, up to n column of A, which are a subset from Rn. These are the coefficient of Rn. Also, we know that let A be an n of n matrix. The orthogonal complement of the row space of A is equal to the null space of A. A row of A, the orthogonal set on the rows, will equal to null of A. This makes sense because we previously succeeded in expressing AX as the columns of the A matrix is a linear combination of the vector space of A. C. Okay. Just a second. Okay. Let's take it in an example. I'll show it to you. So now, for the time being, the orthogonal complement of vectors, which belongs to Rn, are such that V times U equal 0, which means, okay, I'll go through it right now. See, if I'm saying that I have A times X equals 0, and let's, for simplicity, I will consider A at 3 by 3 belongs to R3. So this is R1 numbers, this is R2 values, this is R3 values. X is gonna be X1, X2, and X3. And we, as we saw previously, I'm multiplying the first row by the values and the second by the values of the column and so on, which can be put as the following. X1 equal to the elements of R1 plus X2 times the elements of R2 plus X3 at the element of R3. And in this manner, it's really very simple to show that this vector space, or whatever this vector space, equal to some constant times vector 1 plus another constant, which is vector 2, plus the third constant, which is vector 3. And this is why we can say that the row space is a combination, okay, of the space of A, the linear combination. So any matrix A of X is a linear combination from the span of A. And also, once you try to solve this system equal to 0, it means you will have these two parts multiplied each other and they equal to 0, which implies that the null set, which is the solution for the system of these matrices, is the orthogonal complement on the rows of the column matrix. And that's the statements that's written. Okay, perfect. Okay, so it's written that xyz times R1 equal to 0, xyz times R2 equal to 0, just for simplicity, and to show you what's the meaning that of the orthogonal complement on the rows will equal to the null set of A. Okay, also I have the rank of A equal to the dimension of the column of A and the dimension of the row A subspace, and it will equal to the difference between n minus the dimension of null A. That's a huge statement, by the way. Because if you remark, we have n at the number of unknowns. A dimension of null of A is the number of dependent values in the infinite system if exist. Okay, so if you have null and you have the value of this system, what we mean now is that null A is the number of dependent that really exist, or the values, as we will see. Dimension of row A is the number of equations in the system of equations. Dimension of column A is the number of unknowns in the system of equation after getting the echelon form, as we will see shortly, and it will equal to rank of A. If you look deeply into this equation, if you have a unique solution, for example, you will have the dimension of null A equal to 0. And in this matter, you will have the number of rows equal the number of columns equal the rank of the matrix, which is equal to the number of unknowns. And it's really a very specific and very powerful definition. In order to make things really very easy, or things to be easier, let's go through this problem. He's stating that find the null, okay, space, row and column spaces of A. And this is the matrix that we took or we formed from a basis of R3, which with the first of R4, which with the first vector 1 0 0, 1 2 1 and 0, and the last vector which is 1 4 2 and 0. All I have to do to find the null vector space is simply if I want to have the null vector space, okay, for this matrix, I will have to solve the system which is AX equal to 0. So I really feel more comfortable, and it's exactly the same. Solve this system which is 1 and 0 0, 1 2 1 and 0, 1, okay, 4 2 and 0, which equal to 0 0 0 and 0. I will try to get it as much as possible nearer to an echelon form. So the first step I'm going to do is to multiply this row by -1 and add it on the second row. So I will have -1 plus 2, which is going to equal to 1, -2 plus 4, which is equal to 2, negative times 0 and 0, which is equal to 0. Then I will go again multiplying this second row pivot 1 by -1 and adding it on the first row. -1 plus 1, the result will be 0. -2 plus 1 is going to be -1. Negative time 1 times 0 plus 0, so it's going to be 0. And in a similar manner, I will try to get these numbers to be zeros. So I will multiply by negative, adding it on the third row. Negative times 0 plus 0 is going to be 0. -1 plus 1 equal to 0. -2 plus 2, which is equal to 0. -0 plus 0, which is equal to 0. And the last one is all zeros. Now I can find the relation between x1, x2, and 3, and from it I can extract the null vector space of A, which is simply, I will consider x1, x2, and x3. Let's try to expand it. So it's gonna be x1 minus x3, which equal to 0, then x1 plus 2 of an x3 equal to 0, and this will lead to x1 equal to x3, and I'm sorry, this is x2, this is x2. So x2 will equal to -2 times x3. So if I'm talking about the vector components x1, x2, and x3, which is simply gonna be x3 and then -2 x3 and x3. Taking x3 as a common, I will have 1, -2, and 1, which represent actually the null space. So I can write that null space of A is the set of 1, -2, and 1. This is what's meant by getting null of A. Just simply solving this system or getting this system on the reduced echelon form and trying to expand it, isolating the main vector. So now I have null of A equal to 1, -2, and 1, which is the generator of the vector of the solution set of a vector space for the set of equations. If I want to get the row vector space, the row of A, it's simply, I will have to remark that I have for the first row, this is the pivot of the first row, and that's the pivot of the second row. So mainly the span of this vector space will be simply these two vectors, which is 1, 0, and the negative 1. This is 1, 0, and the negative 1. And the last one will be 0, 1, and 2. So the main row space where 1, 0, 0, 1, 2, 1, 0, 1, 4, 2, 0. And after taking them from this vector space, it's going to be 1, 0, negative 1, 0, 1, 2, as we will see now. Okay? So as I told you, now means the solution set of the system of homogeneous equations. So I will try to solve this system. This is what we mean by NA, solving this homogeneous system. This is the system that we are talking about. This is on the echelon form. So x1 equal negative will equal to x3, and x2 will equal to negative 2 x3, as we saw exactly here, like this. So now the vector that represent the solution set or the null of A, which is 1, negative 1, and 1, 1, negative 1, and 1, exactly the same. So I've just replaced by x3, isolating x3, I've got the span. Remark that the dimension of null A equal to 1. If I want to get the rows, so now remark, this is mainly the rows, okay, of the main matrix, which is 1, 0, 1, 2, 4, 0, 1, and 2. But there is dependency between this set of the vectors that's generating the vector space of A. Once you put it on the echelon form, I will take just only the vector of the first vector and the second vector, which can be taken from the echelon form 1, 0, and negative 1, 0, 1, 2. Here they are 1, 0, negative 1, and 1, 0, 2, exactly like what we did. And also I can get the column span of A, which is span of start looking at the pivots, which states that the first column from the coefficient matrix or from the main matrix of the vector space, and the second column. So simply it will be 1, 0, 0, 0, and the second pivot, which is 1, 2, 1, and 0, as you can see. Yes, exactly as I told you. Look for these, once again, for the rows. These are the rows that we are talking about. As you can see, it can be reduced to the span of 1, 0, negative 1, 0, 1, 2. Also, remind that we have dependent vectors here, so we isolated one of them, we're taking out one of them, and we took the final rows from the echelon matrix. These are the repeated ones. See, I will take the first row and second row, which stand for the span of rows. For the columns, it's exactly the same. This is the first, second, and third. For the span, which represents that I will consider just only for the independent vectors, the first column and the second column. As you can see, the first column from the main matrix, which is 1, 0, 0, and the second one, which is 1, 2, 1, 0. I usually take the span, the independent set of vectors for the row span from the echelon form. But from the column space, I will take the pivots, which indicate the vectors in the main column matrix, which are considered the span of or the basis for the column span. So I will take the first column here and the second column, as you can see. Okay, perfect. This is row dimension 2, and this is the dimension of column. Remark that the dimension of null plus the dimension of row will equal to the dimension of this vector space. This is 1, that's 2, the sum will be 3, as we will see. Still trying to point out that we have these two sets are dependent on each other. So this is why I'm taking just only the pivot for the first column. So I consider the first column, and the pivot for the second column. This is why I've took 1, 2, 1, 0. In this proposition, it's exactly what we said previously in the previous example, that let A be an M in matrix and B a matrix in the echelon form. So you will have to get it in the echelon form first. The non-null rows of V as vectors of Rn, and this is what happened exactly. Now I've taken these two null rows to be the vector space of the row, and the columns as vectors of Rn corresponding to the columns of V with pivot from the basis of columns of A. And that's exactly what happened. We took the pivots and we took the columns, depending on these pivots, pivot of the first column and the second column, took the first column and the second column. Okay, here also he's stating this. For this problem, find the basis for the null row and the column space of A. You want the basis for the null, then for the row, and lastly for the column space. All I have to do once more is to put this form or this set of vectors on the reduced echelon form. Okay, just a second. I would like also to solve it with you completely. Okay, so all I have to do is to get for the first matrix, which is 1, 0, and 0, negative 1, negative 1, and 0, triple zeros, 0, 1, and 0. I will start to try to put it as much near as possible to the reduced echelon form. So it simply will be 0, 1, 0, and the negative 1, multiplying the second row and negative 1. Then I will try to get this number equal to 0. So I will multiply by negative, then add it on the first term. Negative 1 times 0 plus 1 is going to be 1. Negative 1, okay, getting the sum of them, 1 plus negative 1 is going to equal to 0. 0 plus 0, so it's going to equal to 0. Negative 1 plus 0, so it's going to be negative 1. The last row is exactly the same. Now we succeeded in putting this matrix, okay, on the reduced echelon form. I will once more consider this is x1 column, this is x2, x3, and that's x4. And I will try to explain this system of equations as a homogeneous system of equations. So actually I'm solving ax equal to 0, as I told you. I usually more comfortable to put this like that. Okay, exactly right. So I have x1 minus x4 equal to 0. That's the first relation connecting x1 and x4. The second one, which is x2, but then minus of an x4 equal to 0, which implies that x1 equal to x4 and x2 equal to x4. So the vector now is like this: x1, x2, x3, and x4. Now I will start substituting, replacing x1 by x4, x2 by x4, x3 will remain the same, and then I will have x4. Now I can isolate this value. Let me check, maybe I made a mistake or something. Okay, now to proceed, these are the values, exactly right. Okay, multiplying this one by negative 1 and the adding, yes, all set, perfect. So finally we got x1 equal to x4, x2 equal to x4 as I told you. Now I will try to separate the results. So I will write it like this. As you can see, we have just only two variables, and this is the solution set, the final solution set. So what I'm gonna do, I need to see in each coordinate both x3 and the x4. So I will start with x4 plus 0 of an x3. Then I will have x4 also minus 0 x3. in this third coordinate, I don't have x4, so it's a 0 x4 plus x3. And then finally, I will have x4 plus, also there is no appearance for x3, so it's 0 x3. I can separate those two vectors away from each other in order to get the span of the null set, which simply can be done like that. This is x4 for the first coordinate. x4 will appear again for the second coordinate. There is no x4 here, so it's a 0. There is x4 once more. Here we go. For the second set, I will start with 0 for x3 and also 0 for x3, and then I will have just only one of x3, it's righted, and finally I have 0. I can take x4 as a common, so the first vector of this vector space is 1, 1, 0, and 1. The second vector is 0, 0, 1, and 0. And so the null space of A will be simply the set that consists of the first vector, which is 1, 1, 0, and 1, and the second one, which is 0, 0, 1, and 0. These are the two vectors that represent the null basis of A. If I want to get the space of the rows and the space of the columns, it's very simple. From the reduced echelon form, you will find that you already have the vector of the first row and the vector of the second row. So I'm going to write here, okay, you need me to get the row space. This is the row space of A, which is simply ended up having it from the reduced echelon form, which are 1, 0, 0, and -1. This is for the first row. For the second row, which is 1, which is, 0, 1, 0, and -1. This is the first row, and that's the second. If I want to get the column space of A, I will also look once more. I have the pivot of the first row, I have the pivot of the second row, or the first column, second column. This is why I will form the column space by getting back to the A matrix, considering the first column, which represent the optimal base, which is 1, 0, and 0. And for the second column, which is gonna be, because this is the pivot of the second row, of the second column, so I will take the second column, which is -1, -1, and 0. We already go through. Let's go through it once more using this example. So now, once more, he asking me to get the null space of this basis, or this vector space. All I have to do is to solve the system, which is A times X equals 0, which is a homogeneous system. So what we need to do is to get a reduced echelon form from this matrix. Okay, I will start, okay, as I told you previously, this is the matrix. How to put it on reduced echelon form? This must be +1. That value equal to 0, so simply I will multiply -1 and add, and voila, this is the reduced echelon form. Which means that if I have x1, x2, x3, and x4, I will have x1 minus x4 equals 0 for first equation. The second one will be x2 minus x4 equal to 0. And from here, I can get a relation connecting x1 or x2 with x4s. So exactly like what we did in this example, I'm redoing it again. I replace x1 by x4 and x2 by x4, giving x3 as it is, and this is the form. I will try to see x4 and x3 in each coordinate, which is a really simple task. I'm missing x3, so it's 0 plus 0 x3. I'm missing x3 plus 0 x3. I'm missing x4 plus 0 x4. I'm missing x3 plus 0 x3. I've succeeded in putting it in this form. Now, trying to isolate it into two parts. Finally, this is the vector space of null A. This is the basis of the vector space of null A. If I want to get Same way before, like before exactly. If we want to get the row of A, I will take the rows from the reduced echelon form, which 1, double 0, negative 1 for the first row, and 0, 1, 0, negative 2, negative 1, I'm sorry, for the second row. And these two vectors belongs to R4, of course. You have the basis of R. If I want to get the columns space, all I have to do is the reduced echelon form. That's the pivot of the first column, so I will take the first column. And that's the pivot of the second column, so I will take this column. So the basis, the column of A, the span will be 1, double 0, negative 1, negative 1, and 0, as you can see, and which belongs to R3. This is the way that I can get the null space, the row space, and the column space. It's really very simple. Okay, perfect. Now, we saw previously that the dimension of row A plus the dimension of NA equal to N. Let's check if this is true or not. From here, the dimension of the basis of null A consists of two vectors, so the dimension is 2. And the dimension for the rows, also you have two vectors, so it's also 2. 2 plus 2 will be 4. And the dimension, this vector space is of the 4th degree. So most of them belongs to R4. So the statement is correct. Okay? And so, of course, the orthogonal complement of row A equal to null A, we really didn't go through this. That's an explanation of what's written here. Here, what I want to say here to you, that let A be an M by N matrix, and the X belongs to Rn. So I'm solving the system, talking about the system, Ax equal 0. Ax is a subset, belongs to the column of A, because simply, once you try to solve the system A times X, you can multiply the first row, as we explained previously, times X1, plus the second row